Walsh diagrams essentially provide a map for how the energies of molecular orbitals change as a single geometric parameter is varied. And these can be used to assess what the optimal value of that parameter might be. So let's talk a little bit about how one might do that. So you can think of this as basically being a primer for how to solve problems using Walsh diagrams. So we're going to use the following analysis to do this. The first step, and this is actually something that is the same as the first step in creating Lewis symbols, is you need to determine the number of valence electrons. And it seems like a pretty simple thing, but it is going to be the thing that ultimately determines the result that you get for the shape of the molecule. You need to know the right number of valence electrons. Now, I should note in this diagram that there is a 1 sigma g that's not shown on here that's below this. What is that? Well, we're talking about a molecule of the formula AH2, and this A is a second row element. That second row element has a 1s orbital, but that 1s orbital is a core orbital, and it does not participate in any of the bonding. So this 1 sigma g is basically the 1s electrons on the A atom that do not participate in bonding. So when we talk about the number of valence electrons, we really mean just the valence electrons on the A and the 1s electrons on the hydrogens. Okay, so once we have the valence electrons, we need to generate the MO electronic configuration. And we're going to do this for both the linear and bent geometries. All right, because what we want to do is figure out what the electronic configuration is on this side of the diagram and what is it on this side of the diagram, because that's how we're going to compare the two. All right, we then need to assess the total energy of the electrons in those molecular orbitals. So I'm going to say of occupied molecular orbitals. So wherever the electrons end up in the electronic configuration, that determines the energy those electrons have from our molecular orbital calculation, and then we can determine what the total electronic energy is for the function based on that. All right, so then the lowest of the total energies, that is between linear and bent, so the lowest total energy, and this is E as a function of theta, determines what the value of theta is. In other words, is this molecule linear or bent at the equilibrium geometry? Okay, now what I've outlined here is for this very specific case of AH2, you can do the same thing for an AB2 molecule also. All right, the Walsh diagram is going to look slightly different from that, but you'll have a chance to look at some of these in the problem set, and so I hope you'll be ready for that. But the whole approach is very similar to what we're going to do here for hydrides in this case. All right, so let's look at a couple of examples. Okay, the first example that I want to look at is one that involves beryllium. So we'll say beryllium hydride, BeH2. So each of the hydrogen atoms has a configuration of 1s, and it's 1s1, and the beryllium has a configuration of 1s2, 2s2, and this part is the part that will end up down here in the unshown orbital 1 sigma g. So all we care about are these 2 electrons. Okay, so the total valence electrons now we're going to have 1 from each of the hydrogens and 2 from the beryllium, so we'll have a total of 4 electrons in our valence shell. So pretty simple case. Okay, our linear configuration, the next step is to determine the electronic configuration. And in the case of the linear molecule, again, we don't have to worry about this. These are the 1s orbitals. We just have to worry about this one and this one. Each one of these can hold 2 electrons. So we're going to have a configuration of 2 sigma G with 2 electrons and 1 sigma U with 2 electrons. If we were, this is for linear, if we were bent, we would be filling this one and this one. So we would have 2A1 with 2 electrons and 3A1 with 2 electrons. Now, I want you to notice something about this diagram, though. If we happen to be at, for example, an angle somewhere in here, well, actually, the second one that we get is 1B2. So we can also have 2A1 squared 1B2 depending upon the value of theta in doing this. All right, so how would we decide whether this molecule is linear or bent? Well, this one is particularly easy because these energies start off down here and they only go up as we move toward nonlinear geometries. So in other words, the lowest energy in the case of BeH2 is fairly easy to identify, and it's basically a linear angle. So theta equals 180 degrees in this particular case. And that is indeed what we find in general for this. Now, I'll note something in particular about BeH2. If I draw it up here and just draw a standard Lewis structure for it, there are no non-bonding electrons on the beryllium. It has used up its 2 electrons to make these bonding orbitals to hydrogen. And so when we learn VSEPR theory in general chemistry, that also would predict that this is a linear geometry because we only have 2 clouds of electrons around the beryllium. They'll want to be as far apart from one another as they can, so we get a 180-degree geometry. And that's a perfectly fine way to reason this out. However, as we are in a physical chemistry class, I want you to understand that it also comes from considering the molecular orbitals that are formed here and whether or not those molecular orbitals are actually at their lowest energy when they're in a linear configuration versus a bent configuration. All right, let's do one more example just to sort of get all this down. Okay, so this is one example for BeH2. Let's consider an example actually for an open shell sort of species. What I'm going to consider here is NH2. All right, so this will be a pretty reactive species since it has an open shell. All right, now in this case, the hydrogens still have the 1s1 electronic configuration, but nitrogen has 1s2, 2s2, 2p3 as its atomic electron configuration. So the total valence electrons, we're going to have 2 from the 2 hydrogens plus 5 from the nitrogen. So a total of 7 electrons. So this is going to be a little bit different case than beryllium. We have more valence electrons to deal with here. So our linear electronic configuration for nitrogen would be something like this. We'll have 2 sigma G with 2 electrons. We'll have 1 sigma U with 2 electrons. And then up here, this pi U, you'll notice it's just like p orbitals. It is p orbitals, but it can hold a total of 4 electrons in this case where the 2 p orbitals are degenerate with one another. So in this case, I'll have 1 pi u with 3 electrons in the linear case. Okay, when we talk about the bent geometry, what will be our configuration? Well, we'll have 2a2 with 2 electrons, 3a1 with 2 electrons, 1b2 with 2 electrons, and then this 1b1, which is in effect the same as the pi u, and it has 1 electron. This 1 electron doesn't change energy between these 2 possibilities. Okay, this is a fairly straight and flat evolution from linear over here to bent over here. And this electron just doesn't change energy as we bend the geometry of the molecule. So all we really have to worry about are these 3. Now, what we would note from this is that these 2 orbitals, the 1 sigma u and the 2 sigma g, so these two both increase in energy. as you move across. But this 1 sigma u, the 2 electrons in it, will decrease in energy because as it goes down to 3a1, the energy of 3a1 is going to be significantly less than the energy of 1 pi u. Okay, we have gone down in energy. And we've gone down in a steeper descent than these two have gone up. So as a result, what we might infer from this is that NH2 is likely bent. All right, we have one set of electrons that are going down in energy, two sets that are going up but less steeply. So there's going to be some happy medium, some happy angle in here where we'll achieve a minimum. The overall total energy will achieve a minimum. That will almost certainly be at an angle greater than 90 degrees. So we can say that theta will be greater than 90 degrees. But we can't from a diagram necessarily get exactly what angle it might be. We would need a full molecular orbital calculation to do that so that we could compare the energies.